Welcome back, everybody. And in this week's module, we're going to be talking about squares, cubes, their roots, and then also we're going to start to introduce the Pythagorean theorem. Let's go ahead and get started. In this week, we are going to focus on discovering what are squares and cubes, what does it mean to find a root. We're going to find out how do I approximate square roots. We're going to be doing that by hand. And then, of course, we'll start to explore what is the Pythagorean theorem? What can I do with it? So let's go ahead and get started. First off, what are squares and cubes? Of course, when initially you see the word squares and cubes, you think of shapes or figures. Of course, a square being a two-dimensional figure and a cube being a three-dimensional figure. And while those ideas are going to come in handy, that's not exactly what we're focusing on here, at least not in a literal sense. So squares, what does it mean to square a number? Squaring a number simply means that we are going to take whatever that number is, which here I'm going to call x, and raising it to the second power. Of course, raising something to the second power is the same thing as taking that number or value and multiplying it by itself one other time, but that's what we mean by squaring a number. The reason that this relates to an actual square, though, comes about in the way that we find the area of a square. Of course, to find the area of a square, we would simply multiply its length times its width. But on a square, the length and the width are exactly the same because that's the nature of a square. All four sides are congruent. So if I were to find the area of the square, I would take side x times another x, which would be x to the second power, or in short, x squared. Similar idea, of course, works for cubes then. When I say that we are going to cube a number, we're going to take a number, which this time I'll call y, and raise it to the third power, or in other words, take that number times itself two other times, for a total of 3 altogether. Now, of course, that relates to a cube because if we were going to find, say, the volume of this cube, we would take one edge length times another edge length. That would help us find the area of the base, times the height of this three-dimensional figure. So volume would simply be y times y times y, which is the same as y to the third power, which again we rephrase, as y cubed. So the exponent of 3 could be y to the third power, or we could say y cubed. The exponent of 2 is the second power, or squared. So those are what squares and cubes are. Over time, you'll actually learn to memorize some of the most popular squares and cubes, and this information is also available to you in some charts, both in your notes and lessons in Canvas, as well as in a PDF document that I've attached in our module this week, but we'll just review some of the easy ones or the simpler ones here. For example, if I asked you what 2 squared is, or 2 to the second power, that would of course be 2 times it itself, which means that 2 squared is, of course, 4. And we could do this with a lot of numbers, 5 squared. We can even do this with negative numbers. We could do negative 7 squared as well. Of course, 5 squared would just be 25 because 5 times itself is 25. When we have negative 7 squared, though, that would be negative 7 times itself, which would be positive 49. I could change one other small thing and place that negative, for example, from the same problem we just did. Place that negative outside of the parentheses. Oops, I've got one too many there. And still square it, but what's important to take note of is that that exponent only applies to the immediate item that it's connected to. So what this is really asking us to do is to take the opposite of, that's another way to read a negative symbol, the opposite of 7 squared. Well, first then we would take 7 squared, which is 49, and then the opposite of 49 would be negative 49. So normally, or in most simplistic situations, you can't have a negative outcome unless that negative has been pulled out in front of a set of parentheses like this. Now, looking at our cubes, please keep in mind that taking the cube of a number can end up with some very large results very, very quickly, which in some ways would make sense. We're multiplying a number times itself 3 times instead of only 2, but sometimes that can still feel a little misleading. So we'll just see some quick examples. For example, 1 cubed, Well, that's simply put still 1, because 1 times 1 times 1 is 1. But as soon as we get to 2 cubed, that would be equal to 8. 3 cubed is equal to 27. If we even were to compare to something like the base of 5 we used a moment ago, 5 cubed is already 125. So the numbers, the solutions start to get large very quickly. Don't let that be too terribly off-putting. Next, we'll take a look at what does it mean to find a root. So we need to understand what a root is. And of course, we're not referring to roots of a tree or a plant. These are mathematical roots. And roots are actually related to powers themselves. So what I want to revisit first is the term inverses. Inverses here. Now, inverses are an idea or a term that we use a lot when we talk about equations. For example, when we solve equations, if the equation involves some addition, in order to solve that equation, we know that the inverse operation we would use is subtraction. So addition and subtraction, those are inverses. Of course, if we had an equation that used some multiplication, we know that we could use some division, or vice versa, because multiplication and division are inverses. Well, now that we're upgrading our skill set a little bit more, what we should know is that powers, in other words, the exponents like squares and cubes that we just saw a moment ago, powers and roots are inverses. So if you had to undo an exponent or a power, you would end up using a root to help you do that. So that's what it means to find a root. But now let's see, what does it actually look like? Well, if you were asked to take the square root of, say, the number 25, what you would see is a symbol something like this. That almost represents, or I'm sorry, it almost resembles the division house that we're used to seeing from earlier grades, but of course this has a drastically different meaning. Let's start by handling a little bit of vocabulary. First thing what we see here is that this symbol means to take the square root of 25, of course. There are parts and pieces to this, though. What I mean is that this symbol here, the one that looks something like a division symbol from before, that's something we call a radical sign. So while we could read this as the square root of 25, we could also read this as radical 25. And that does mean that with that 25 being under the radical sign, it does get a special type of name. We refer to this as something called a radicand. And again, that's just the number that we're taking a root of. Now, there are different kinds of root symbols as well. For example, if I wanted to take a cube root instead of a square root, we would do the same type of symbol, but we would also add a small superscript 3 right here in the front of it. If you were going to take a fourth root, you do the same thing. You'd use the root symbol or the radical sign and put a small superscript 4 right up here. So you can take lots of different kinds of roots, and that should make sense because we have lots of different kinds of exponents as well. When there is no symbol at all, similar to what you see here, it is implied that it's automatically a 2. We just don't write the 2, and that's what it means when we say that it is implied. With that in mind, when they ask us to find the square root of 25, we're being asked to process what number times itself would equal 25. And it's just that one number that we're looking for. Of course, most of us are aware of the fact that 5 times itself equals 25. So we would say that the square root of 25 is equal to 5. Now that's also step 1, but what we have to keep in mind is that there's actually another answer as well, and that goes back to what we know about integers, because not only does 5 times itself equal 25, you might want to keep in mind that also negative 5 times itself, negative 5 times negative 5, that also equals positive 25. So which one are we supposed to use? Well, while we won't do a terrible lot of this right now, what we're actually going to do is keep in mind that we could actually have both numbers as an answer. The square root of 25 is actually both positive and negative 5. So we'll use that symbol occasionally, where we use both a positive and a negative symbol to say that both are options. However, sometimes the solution will be situational or based on the context of the problem, meaning it might have to be a positive or it might have to be a negative based on the situation. So taking a root, simply saying what number times itself would equal the radicand. Now, so far, all we have seen is something called a perfect square. And the perfect square is just a number that is the result of two integers, or I'm sorry, an integer being multiplied by itself. For example, if I took 2 times 2, of course, that would be 2 squared, which is 4. 4 is a perfect square. And in the chart that I mentioned is in your module, you've got a list of a lot of perfect squares. And really, again, all that's asking you to do is take 1 squared, 2 squared, 3 squared, oops, squared, there we go, 4 squared, and so on. And the results of that process, the results of those powers, those numbers, those are our perfect squares. Those are helpful to identify though, because when you take the square root of a perfect square, you get a nice clean whole number. What I mean is if, for example, you took the square root of 4, you're going to get a nice clean whole number like 2. You take the square root of 9, you're just going backwards, you're getting that base of 3. You take the square root of 16, which is 4, again, because those numbers times themselves equal the radicand. However, what happens if you take the square root of a number that is not a perfect square? For example, what if I wanted to take the square root of a number, say like 11? Well, there is no number when, I'm sorry, there is no whole number, no integer when multiplied by itself that will equal 11. So what do we do in that situation? Well, the first thing we're going to learn to do is we're going to try and estimate the answer using a skill set that we can do by hand. It's a little bit of a confusing process at first, but with some practice, you'll get much, much better at it. So how do we approximate a square root of a number that is not a perfect square? The first thing I'll tell you is that it'll be very useful for you to become as familiar with perfect squares as you can be. And this is in your notes and lesson. Again, it's in that document in your module. The more familiar the more familiar you are with recognizing those symbols, the easier this process will be for you. I'm sorry, not symbols, recognizing those numbers. Try that. The easier this will be for you. For example, perfect squares, the first several are 1, because 1 times 1 is 1. 4, because 2 times 2 is 4, and then 9, 16, 25, 36, 49, and so on and so forth. Okay, the more capable you are of identifying those quickly, the faster you're going to be at this process. Okay, let's get into it. Step 1. What you guys are going to want to do are list the two closest perfect squares to the radicand here. You're going to want to find the closest one smaller than 11 and the closest one that is larger than 11. Here's what I mean. The closest perfect square that is smaller than 11 is 9. 9 is a perfect square because 3 times 3 equals 9. The next closest largest perfect square would be 16 because 4 times 4 equals 16. There are no perfect squares between 9 and 16, so we know we've done a good job. Again, we know that 11 is between 9 and 16, and that's why we chose those perfect squares. Next, we're going to go ahead and find the square roots of these perfect squares. So we'll find the square root of 9 and the square root of 16 and write those down. The square root of 9 is 3 because 3 times 3 is 9, and the square root of 16 is 4 for the same type of reasoning. After that, we're going to identify the perfect square. So right now, those options would be 9 and 16 because those are the two I chose. We're going to identify the perfect square that is closest to our radicand that we are concerned with. So in other words, we're asking, is 9 closer to 11 or is 16 closer to 11? Well, 9 is only 2 away from 11. That's their difference. 16 is 5 away from 11, so that's a little bit further away. 9, that is the closest perfect square. That's going to be important. That's going to come back later to help us. So we are going to find the difference between those two, which we already did. So keep in mind that these numbers are going to come back to be helpful for us in just a little bit. First thing we're doing is again trying to estimate square root of 11. Right now, I'm actually part of the way there because we've now identified that the square root of 11 has to be somewhere between the square root of 9 and the square root of 16, which means, again, that the square root of 11 is somewhere between 3 and 4. So if we were actually to use a calculator or another means to find these square roots, we would end up with 3 point something. Okay, now we're going to get a little bit closer than just 3 point something, and here's how we're going to do that. We are going to go ahead and find the difference between the original radicand and the closest perfect square. We've already done that here. This becomes the numerator of a fraction that we're going to create. Next, we're going to find the difference between both of the closest perfect squares that we identified from the beginning. That means the difference between 9 and 16, and ask ourselves, what is the difference or the distance between those two numbers? And of course, the distance between 9 and 16 is 7. This becomes the denominator in that fraction that we are creating right now. Next, we're going to convert our fraction into a decimal. Just as a reminder, to convert a fraction into a decimal, you can go ahead and do the long division if you feel successful at that, or this might be a good time to simply grab a calculator and type in numerator 2 divided by denominator 7. Now, in some cases, you'll get a nice clean decimal, perhaps. In other situations, you might get a repeating decimal or an otherwise never-ending decimal that does not repeat. In this case, that's what happens. And we find out that 2 divided by 7 is approximately 0.29, but I've rounded up to the hundredths place. We're going to approximate our square roots to the nearest tenths place, which means I'm going to round this to this place value. 0.29 would round to be 0.3. So we took our fraction, we converted it into a decimal, and rounded to the nearest tenths place. This is going to be helpful for our last step. We already said a little bit ago that we already identified early on that the square root of 11 had to be somewhere between 3 and 4. And then we even said that we knew that it would be, of course, then 3 point something, because that would keep us between 3 and 4. But we have to now identify, what do I do with this extra decimal that I have? Do I add it onto the 3, or do I need to subtract it away from the 4? What version of that should I be closer to? So we're actually going to go back up here to around this step when we identified which perfect square was closest to our radicand, and we said that that was 9. Here's the rule for whether you add to these numbers or subtract from another one. If the perfect square you chose was less than the radicand, then we simply add the decimal on to the first number. If the perfect square we had chosen was more than the radicand, we would go ahead and subtract away from the upper value here. Of course, in our situation, we chose 9. That was the lesser of the two perfect squares, which means that we're going to take our lower value, which was 3, and we're going to add our estimated decimal, which is 0.3. And we should find that the approximate square root of 11 is about, let's get the about symbol, about or approximately 3.3. Now, you'll also get to use a calculator later on for some more specific situations, but it's important that we identify how to actually calculate some of this by hand for a variety of reasons that you'll see as you guys work through these sections. The last thing we'll talk about for this module is what is the Pythagorean theorem, and we're just going to get a brief introduction to that here. So the Pythagorean theorem is a mathematical idea that we'll explore that helps us find the distance between 2 points. And for our purposes, that distance is going to be explored by using right triangles to help us. It is important to note that the Pythagorean theorem only applies to right triangles and not other types, which is something that you'll be asked to explore a little bit later on. Now, the theorem simply says this: a squared plus b squared equals c squared. So obviously, you can see why it's important that we started off with perfect squares and things of that nature here. And you'll see later on in your own exploration why square roots are also going to be valuable to us. But before we wrap up this video, we're going to explore a brief proof of why this a squared plus b squared equals c squared idea works and what the letters mean. The first thing I would like to point out to you is what a, b, and c represent. A and b both represent what we call the legs of a right triangle. The legs are always going to be the shortest sides of the right triangle, and they're actually the two sides that meet at the 90-degree angle that creates the right triangle. C represents something we call a hypotenuse. And a hypotenuse is the longest side of the triangle and is also the side that will also be directly opposite of that right angle. So we're going to take a look at this proof here in just a moment and point out some of these sides, but let you see a little bit more about why this theorem exists and how it helps us find this distance. So here we have a right triangle. You can see the right angle in the lower right-hand portion there. First thing we're going to identify are the A, B, and C sides of the triangle, or the legs and the hypotenuse. Keep in mind that the legs are the two shorter sides. So here I'm going to label this side A and this side B. Before I continue, A and B are actually interchangeable, and there's really no difference between which leg of the triangle you call A and which one you call B, as long as you make a choice. That, of course, leaves the final side, or the longest side of the triangle, which is the hypotenuse, which we call C. So here's what people have discovered, at least here's one version of what was discovered, into how these three sides will relate. If I were to extend a square from each side of the triangle that matches that side length, we'll find a relationship that connects all three of those squares. Those squares would look something like this. And looking at each of these squares, we could go ahead and find those areas. So I would need to count the unit lengths of each side. For example, A here has a length of 6, so each side of the square is 6, and side B was actually 8 units long, which makes each side of the square 8 units long. And we'd want to compare those areas. Now, of course, to find the area of a square, it's just length times width. In this case, they're the same. So for example, to find the area of the A square, that would just be 6 squared, which is 36 square units. And for the B square, that would be 8 squared, or 64 units. And I'll already go ahead and tell you, I think, that side C was originally 10 units, which means that the area of the C square would be 10 squared, or 100 square units. So when we look at the Pythagorean theorem, which says that a squared, or the a square, plus b squared, or the b square, has to equal c squared, this is exactly what we're referring to, because if we take the a square, which is 36, plus the b squared, which is 64 square units, it should equal the c square, which is 100 square units. And in fact, if we double check things here, 36 plus 64 is 100, and 100 does equal 100, and it works out. Now, while you won't always be finding or applying these ideas of squares, this is one way to prove the Pythagorean theorem can in fact work, or does in fact work, we should say. What you're going to do over time is you're going to learn how to apply this Pythagorean theorem to, as we mentioned at the beginning, find the distance between a variety of points. Now, some of you might wonder, why would I need the Pythagorean theorem to find that distance? And it actually goes back to us talking about side C, which is right here. Side C being this, in this case, what appears to be a diagonal side, it's very difficult to measure, and especially measure precisely. The Pythagorean theorem solves the problem of being able to measure those diagonal lengths. Now, that side of the triangle then can be applied in a bunch of different scenarios, which is what you guys are going to learn to do. You're going to learn to use the a squared plus b squared equals c squared, and right triangles in a variety of different ways to help you guys explore that idea. So those are just some beginning thoughts and just a beginning explanation of what you guys will see. But hopefully it gives you lots to think about before you go to take your notes and before we take a closer look in our virtual classes. Good luck with everything as you start off the week, and I will talk to you guys soon.